You ready to go? Okay, well, it's my pleasure to introduce Jean, who's just on his very last day of his internship on the Bridge Day, with some really interesting results around GBDTs. So yeah, go for it.
Thank you, David. I will present what I've done during my research internship at Kiteo. It's my last day today, and it was a 6-month internship, which started in May. So this presentation summarizes what I've done during the internship. It was my end of study internship for the Master 2 Data Science from Institut Polytechnique de Paris. During the internship, I was part of the recommendation team within the research department of Kiteo, under the supervision of Sergei Ivanov, which left a bit early, unfortunately. The topic of the internship was higher order optimization for gradient boosting decision trees. And the goal was to make a more efficient training of GBDTs for better efficiency and understand the behavior of this new class of GBDT models that we introduced. So let me walk you through what I will cover in this presentation. So in the first part, I'll talk about gradient boosting and higher order optimization for gradient boosting. In the second part, I'll cover what we have done experiment-wise during the internship and what are the results. In the third part, I will walk you through some of the follow-ups of the project and what could be done and what is there to get on with the results that we have. And finally, I'll let you have questions if you have any. So higher order optimization and gradient boosting. Just as a reminder, I wanted to fix ideas on the framework of the problem. It's the classical supervised learning framework. And the goal of supervised learning is to find a good approximation between inputs and outputs without any knowledge on the dependency that we have. So the goal is to find a mapping from the space of inputs to the space of outputs. Here it's this phi, which gives us a correct approximation of the outputs desired. For classification tasks, there exists a very natural way to measure how well does our approximation perform, which is the generalization error, which essentially tells us in terms of probability how much our model is wrong. This error can be written in terms of expectancy. And one way to see this expectancy term is to introduce this indicator function as a loss function. And therefore, not only for classification, but for more a broader class of problems, the task of supervised learning is to minimize this functional L of phi, which is the expectancy over our space of inputs and outputs of the loss of our prediction with regard to the outputs which is desired. And our goal is to find a function which minimizes this functional in the class of function that we are considering. A brief word on boosting. Boosting was introduced historically as a way to combine weak learners together in order to create a strong one. So the classical example, which was proposed in the 1990s, was to say, okay, we have a class of we have 3 weak learners, and we want to create a stronger one by combining them in a smart way. So the way it was done, say, okay, we train a first classifier H1 on n points of a data set G. We train a second classifier on n new points, among which half were misclassified by H1. And we train a third classifier on n points on which H1 and H2 disagree. And the outputs, the final classifier, will be the majority vote of the those three first classifiers. And it's a voting algorithm, and the key results is that the new classifier is more accurate than H1, the original one. So in a more mathematical sense, there's been a bridge between boosting and gradient descent further in the 1990s with the development of the theory revolving around it. And it has been discovered that gradient boosting actually mimics gradient descent. However, the optimization process is not parametric, and it's directly in the functional space. So in the classical parametric gradient descent, which, for example, is used for training neural networks, we put a parameter space on our function. So our function is parameterized by a value theta k, and at each iteration we will modify this parameter by taking the gradient with respect to this parameter, adding a step size, and changing our result from the previous iteration to go in the direction of the gradient. In functional gradient descent, we do not have this parameterization, and therefore we are directly optimizing in the functional space. So our new function would be a corrected version of the previous one with a gradient-like value, which is estimated as being near the gradient with respect to the function of the last iteration of our functional at points of the function at the last iteration. So this is the key difference between gradient boosting and classical parametric gradient descent, and it leads to algorithms which are a bit different in its core. Let me quickly remind you how we use classification and regression trees. So I have built these figures which show a classical classification or regression tree. So we have nodes here, and we have at each node a feature to perform a split, and a split value which decides regarding this feature if the instance, the data points, go to the right branch or go to the left branch. So in this example, I took 3 data points, and for these 3 data points, they have different paths across the tree, as by doing the computation with the chosen split feature and split value. So now, gradient boosting with trees. How do we do gradient boosting with trees? At each step, we are trying to build a new tree to improve the current model. So here is a plot to explain how it works. So we have the x-axis is the number of iterations. The y-axis is the error, And at each iteration, we are trying to add a new tree in order to improve the model from the last iteration. And at each iteration, the model which is being used is a sum of all the trees built until step T. At each step, our goal is to optimize, given a loss function L, this functional here, which is the sum over all the data points of the loss of the true label of the instance, the prediction from the last step, plus a correction, a new tree, xi, and we are trying to optimize this functional, which essentially means that we want to correct the predictions from last step in order for it to be more accurate in the next step. However, one problem arises. Indeed, finding this arg minimum over the space of trees is an NP-hard problem if we consider a certain specification of the class of tree that we are looking at. So one way to deal with this problem is to use a greedy growing algorithm, which essentially means that we are going to build iteratively a tree and trying to minimize this value here step by step by at each time dividing our final nodes, our leaf nodes, into two lefts and rights nodes in order to improve the precision that we had before doing the split. So in more mathematical terms, if we consider splitting one node, we consider each possible splits, which means choosing a feature to perform the splits and a split value for this feature. And we are trying to find the minimum of the loss prediction, which is the loss after the splits minus the loss before the splits over all the split candidates that we are looking at. Here, equation 7 is a discrete optimization problem in the sense that we are iterating over all split candidates. However, on the right side of 7, the loss terms are also a solution of an optimization problem, which is stated in 8, and which is to minimize the value of the loss inside the terminal node. So this is a continuous optimization problem. So the key takeaway is the two following points. We have a heavy combinatorial optimization within which there are two convex optimization problems. So the main goal is therefore to find a way to solve 8 very accurately and very fast to have a very quick search over the possible split candidates. So how do we do this? So this was the core of the topic of my internship. To do so, we can do an approximation of the loss that we are trying to optimize. We use this classical theorem, which states that as we have a convex problem, finding the minimum of the loss function is equivalent to equating its derivative to 0. And one way to make this problem easier is to do a Taylor approximation of our loss on one node to order P. So we use a Taylor approximation. We can regroup the terms in a more standard way. And we have a new approximated optimization problem, which is equating this derivative to 0. And this derivative is a univariate polynomial in omega. So let me talk to you about higher optimization now. So until now, state-of-the-art gradient boosting libraries used p equal to. It results actually in some kind of a Newton method, which is not exactly a Newton method, but it's we see that there's similarities between this formula and the Newton method. And we obtain an optimal weight for the terminal leaves, which is specific to this approximation of the loss to order p equal to. However, what we can do is go further into the approximation of the loss, and we can use Hauser's weights, which comes from optimization theory, and is a formula to find the zero of a polynomial of order p or of order. It is not an exact method, obviously, but it's a good one-shot method. It's a good one-step method, and it finds accurately a solution to the optimal point, which is more accurate than the other two. So here I've put up the Hausser weights that we get for p equal 3 and p equal 4, which we have used in our implementation further. With this new optimal weights, we get the corresponding approximated loss value in the combinatorial optimization problem that I've shown you before, and therefore we can find the optimal split candidates with these approximated optimal loss value, which correspond to these optimal weights. Now, let me walk through the experiments that we've done. So for the sake of implementation, we chose to go with PyBoost, which is a Python-based research tool for exploring GBDTs. It was actually quite a challenge to choose how we were going to go with implementation, as many of the implementations of gradient boosting decision trees are very heavy and pretty difficult to modify. And we had the chance to find this PyBoost and to work in collaboration with the developers of PyBoost. PyBoost used computation with GPU with the QPy, which is a Python interface for CUDA. So regarding the experiments, so after implementation, we used 4 classification datasets. We trained the second order model for 10,000 trees, recorded the best test accuracy it achieves, and measured the running time it takes to reach 99% of the best accuracy that we've found for the second order. Training was performed on Criterio machines. Here are the specifications if you want to take a look at them. And one point to state is also that higher order GBDTs are more sensitive to regularization factor lambda, and we selected it among a range of lambda values from 1 to 1 million. So here are the results. In the first place, I want to talk about this table. So this table is a summary of the running times for each of the algorithm for second, third, and fourth order optimization versions. And we have the recording of the time for each data sets and the gap in terms of percentage regarding the baseline value, which is the second order. And so for with third and fourth order optimization, we get a tremendous acceleration for convergence, and we get up to 73% acceleration. And the mean for third order is 44% acceleration in time. And for fourth order, it's up to 44.5% of acceleration. So this is for the running time. And here I plotted two plots of the test accuracy metric for two data sets. So for each plot, we have the second order version, the third order version, and the fourth order version. And we can see that there's a clear acceleration in training, and when we are going higher in the optimization order. Regarding hyperparameter tuning, I've stated that the higher order version of the algorithm is more sensitive to the lambda parameter and is more prone to overfitting. So this is shown in this bottom graph here. So I've plotted in blue the second order version, which is the baseline here, and different value of lambda for the third order version. And we can see that in this case, it's overfitted very badly, even though at the beginning it was optimizing way quicker. On the train test, however, we can see that third order performed very well and optimizes way quicker. So the outcomes of these experiments. First of all, the experiments reflect that higher order optimization speeds drastically the training for a target accuracy with about up to 50% acceleration in time and across different data sets. However, regarding the regularization, higher order optimization has demonstrated to be more sensitive to the regularization parameter. And it seems like it's not suited for regularizing these higher order methods. So what's next for this project? I think the first point is finding a proper regularization for higher order methods. So from the optimization literature, we could incorporate higher order penalization terms, such we've used the L2 norm here for penalizing in the optimization problem. We could look at what happens with L3, L4 penalization. And in terms of statistics, include bagging and other variance reduction methods to leverage this overfitting behavior and give it its full power to a higher order optimization. On the theory side, it would be interesting to get convergence bounds. So this is more on the optimization point of view, and do a connection with statistics and optimization theory, which were the founding domains of gradient boosting. And third of all, it would be interesting to understand how these apparently more efficient methods could be integrated in machine learning pipeline and how it could help for large-scale computing. Well, that's it for me. I thank Criteo for hosting this internship. I'm very thankful for the recommendation team and all the great people I've met during my internship. I thank Sergey, who is not here today, but he's been a very great mentor. And I thank you, David, for taking the lead when Sergey was gone. And yeah, it was a great time for me during those 6 months, and I hope my work will be helpful.
Well, thanks, Sean. Apparently, Sergey's camping, so that's why he can't join. Are there any questions? Must be very clear. Are you yourself thinking about doing any further work on this project now that you're free? You know, you're from Criteo. Is it something you personally want to develop, or if you find a PhD in an academic setting or something that you think there's more, like 50% improvement at speed sounds not nothing.
Yes, definitely. Well, there are some opportunity at the moment in the GBT research community, as it's very powerful and very helpful, especially for tabular data. However, I didn't come across one that's matched my let's say my work for the moment.
Yeah, the different topics.
Yeah.
Okay. Anyone else with it? Sorry.
Oh yeah, sorry. I was about to ask a question, but go ahead.
No, yeah, I was about to ask a question, so please.
Okay. Yeah. Just was just curious about your last point and your conclusion. You said that it would be interesting to explore how it could be possible to integrate in ML pipelines with large scale computing. What do you think are the challenges there, like parallel training, things like that? Or I'm just curious.
Yeah, so I think one of the strengths of gradient boosting is that it's very universal, and there's not too much hyperparameter tuning to do, and you can just train models for it to. I mean, you can just easily train model, and it's very efficient. Here in the experiments, higher order optimization, the higher order optimization version have shown to be way more prone to overfitting and very well difficult to tune. So I think it crosses the previous points, but understand. I think there's the goal would be to find a way for it to be universal, the higher order version to be universal and easier to use in practice.
Yeah. Okay. Is there like any challenge about like maybe I missed it, but in your experiment did you use like a single GPU or multi GPU training, or is there two GPUs? Yeah, sorry.
Yeah, so we used two GPUs and yeah, so here are the specs.
Okay.
And
so
it's GPU training.
So it's easy to parallelize.
Yeah, definitely. Yes,
okay.
It's very easy to parallelize.
Yeah, cool. Thanks.
Yeah, maybe a related point. Your I would expect, as well as being faster, your trees are going to be smaller.
Yes.
Have you got some feel of how are they a lot smaller?
So I don't have the numbers here, but here on the plots, each iteration corresponds to building a new tree. So if we have a faster convergence, if we want to have, like, for example, on this epsilon data set, 85% of accuracy, the number of trees of about 125, whereas it's about 250 for the second order version. So I think the time acceleration is pretty proportional to the iteration acceleration. So yeah, so we would have about like probably around minus 50% complexity reduction in the model. Yes.
Okay, cool.
Jean, I still have a question, please.
Yes.
Can you just go back to the previous slide, for example? Did you ever think about maybe because like in GBDTs and in symbol trees, we use actually trees to have some like a model that is interpretable, right? It's really easy to interpret the results with trees. So like what I'm trying to say is like maybe if you only need 3 or 4 trees to get 85% accuracy, it's a result that is easily interpretable compared to 100 trees, for example, right?
Yeah, I follow you. Yes.
So like you can use these results also to have a more interpretable model than like higher order GBDTs give you models with the same accuracy and more interpretable.
Yeah.
Because you only have like fewer trees, so you can easily explore the trees there.
That's a very good point. I'm not too aware of interpretation of gradient boosting. I know there's a work going on. It's a research topic. But yes, I guess if you have fewer trees, you probably gain in interpretability, I guess.
Thank you.
Any last questions? Okay, well, thanks again. That was really great. So I'll clap for you, for everyone. Yep. All right. And maybe we should catch up in a minute.
Yeah.
But thanks. That was really cool.
Thank you, everyone. Thank you so much.
Thank you. It was great having you.
Thank you.
Thank you.
Bye.
Bye.